Hello, welcome back. Today I want to talk about Prim's algorithm and minimum spanning tree. What is a spanning tree? It's a minimum subset of edges that's needed to connect all the vertices together in a connected graph. For example, in this set of vertices, this will be a spanning tree. This is also another spanning tree, and this one is not a spanning tree because we can delete this edge and then all the vertices are still connected. So what is the minimum number of edges we need to connect n vertices in a connected graph? If we have one vertex, we need 0 edge. If we have 2 vertices, we need 1 edge to connect the 2 vertices. If we have 4 vertices, we need 3 edges. So we need a minimum of n-1 edges to connect n vertices. When we talk about spanning trees, we are often working with a connected and edge-weighted graph. Let's take a look at this example. This will be one spanning tree. If we add the weight of all the edges together, this will have a combined weight of 6. Here is another spanning tree of the same graph, and this has a combined edge weight of 5. And here will be another spanning tree, and this has a combined edge weight of 4. A minimum spanning tree is a spanning tree that has a minimum combined edge weight. So this one would be the minimum spanning tree of this graph. If the combined weight is maximum, then we have a maximum spanning tree. The minimum spanning tree or the maximum spanning tree, they don't have to be unique. One can have multiple distinct minimum spanning trees for a particular graph. To summarize so far, definition of minimum spanning tree is a set of edges to connect all vertices in an undirected graph such that the combined weight of all edges is minimum. Now let's talk about Prim's algorithm in constructing a minimum spanning tree for a weighted undirected graph. First, we start with any node. The second step is to add the minimum weight edge to the existing tree such that the edge must extend to a new node. Let's construct a minimum spanning tree for this example. First, we start with the node A. This can be any node, but we just start with node A. And then we will extend from node A to a new node. We can have the possibility of A to C or A to B. Both have a weight of 1. So let's say we pick A to B. So we constructed this new edge. Next, from A to B, we can have the possibility of AC, which has a weight of 1, or BC, which has a weight of 2. We will pick the edge with the lower weight. So we will pick AC. So we add this to the tree. Now the tree has 3 nodes, A, B, and C. To extend to a new node, we can either add CD or CE. CD has a lower weight, so that's the edge that we will add to the tree. Now the only node left is E, so we can either go CE or DE. DE has a lower weight, so that is the edge we will add to the tree. With the inclusion of vertex E, we have now connected all the vertices in the graph. With 4 edges connecting 5 vertices, we are completed building a minimum spanning tree for this graph. Now, a few notes on the implementation. We use a heap to store and sort all the edges with weights. And we use a hash set to store all the visited nodes that's currently in the minimum spanning tree. Now let's do a real example together. This example is from HackerRank. I left the links below. Essentially, we are given a graph, and our job is to find the combined weight of the minimum spanning tree for this graph. The example they provided has 3 nodes and 3 edges. The minimum spanning tree for this example is this one, and it has a combined weight of 4. We are given the number of nodes in the graph, and we have a list of edges, and the list is such that the first and second elements are the nodes of the edge, and the third element is the weight of the edge. So for example, 1, 2, 2 is an edge between 1 and 2 and has an edge weight of 2. This implementation is in C#. I provided the code in the GitHub links below. We start with several data structures. First of all, I will use a hash map to store the adjacency list of the graph. And also, I will use a heap, and the heap will store a tuple with the nodes and the weight. I will use a hash set to store all the visited nodes. So first, I will iterate through all the edges, and then I will populate the adjacency list. As this is an undirected graph, so there will be 2 entries. So for example, in the first edge, I will have 1 and 2 here. 2 is the other nodes, and then the other 2 is the weight. And then I would also have 2, 1, 2 here, meaning that the 2 nodes connects with 1 and also has an edge weight of 2. So after the for each loop is done, the adjacency list will look like this. Next, I will put in the queue the starting nodes and the weight at 0. I will initiate the variable total weight, and that's the variable that I will return at the end. Using a while loop, I would dequeue all the tuples that are in queue in the heap. The first tuple that I would dequeue is the starting node, which is 1, and then I would check whether the visitor set contains the node 1, and it doesn't. So I add this to the visitor set, and I update the total weight. In this case, is 0. And then for the number 1 node, I would check the adjacency list, and I will add all the vertices that are connected to 1 to the heap. So as you can see, 1 connects to 2, and it connects to 3. So these tuples go into the heap. Because the heap is prioritized by the weight, so the top of the heap is the 2, 2 tuple. So once I dequeue, 2 goes into the minimum spanning tree. Because the 1, 2 edge has a weight of 2, I will update the total weight here to be 2. I add the 2 to the visited set. Now, for the 2 nodes, I check the adjacency list, and I add all the edges that's coming out from 2. So as you can see, the possibilities are 1, 2, and 3, 2. Now 1 is already added in the visited node, so I would not put that in the heap. 3, 2 on the other hand, because 3 is not in the visited set, so I would add 3, 2 into the heap. Again, the heap prioritized by weight, so the top of the heap is the tuple 3, 2. So I dequeue that, I add 3 to the minimum spanning tree, and I will add 3 to the visited set. The weight of this edge is 2, so I update the total weight to be 4. For the node 3, the possibility is 1, 3 or 2, 2. Now both 1 and 2 are already in the visited set, so these tuples are not added. The only tuple left in the heap is 3, 3. So in the next iteration of the loop, 3, 3 will be dequeued, and I check that 3 is already visited, so I will do nothing. And then this while loop will finish, and I will return the total weight as 4. Okay, let's talk a little bit about the time complexity. When we iterate through all the edges in this part of the code, the time complexity is O of E, where E is the number of edges in the graph. When we go through all the edges in a heap, that is has a time complexity O of E log E. This is the dominant term, so totally time complexity is O of E log E. Now, we can also track the number of edges that we have added to the minimum spanning tree. Remember, all we need to add is n-1 edges. That is something we can add as an optimization. Okay, let's take a look whether this works. And it looks good. In the next video, we'll use Prim's algorithm to solve a similar problem. Hope to see you then.